Hello, everybody. Now we're going to discuss one of the factors that cause kind of more pressure drop or head losses than usual, which is the pressure drop in the entrance region. I'm going to start with an explanation what we mean by the entrance region and to see how the nature of the entrance region affects or causes pressure drop more than usual, and understand some related concepts like the boundary layer. So the entrance region, we mean by the entrance region that the fluid, when it or the behavior of the fluid as it enters the pipe or the tube where it's flowing through. So let's say this is a side view of a pipe and the fluid is just entering the pipe. So it's the moment here at the very end, very beginning of the flow as it enters the pipe. So it's still not affected by the pipe that is flowing through. So let's say it's coming from a very large tank and then it's going through this pipe. So as it goes from this large tank to the pipe, it starts to in the beginning, as it starts here, it starts as normal flow. It's not yet affected by the friction with the walls of the pipe and the shear force with the walls. So the velocity profile will be something like this, that it's the same velocity everywhere. As it moves forward inside the pipe, we know that the no slip condition always applies. So this means that the layer of the fluid that is in contact with the inner wall of the pipe here and here will go to a full stop or complete stop. So the velocity here would be 0 and the velocity here will be 0. Okay, and you can think of this fluid as it goes forward as if it's like molecules that are sticking to each other or they are held with a rope or something like this, and the reason is we know that, or we deal with the fluid as parallel layers, and as they are flowing, of course this is for the laminar flow, and as they are flowing past each other, there is shear force that takes place between the layers of the fluid. So as the fluid moves forward, this layer goes to 0, then there is shear force that is starts to happen between the surface and the layer, or the layer at the surface and the adjacent layers, and this will cause the velocity to be less as it goes forward until it reaches a point where it's not yet affected by this. Of course, this happens on both sides of the pipe. Okay, and as it moves forward, the effect of the shear force at the wall starts to be more felt in the layers further from the wall. So it gets more I mean, this increase in the velocity becomes over a wide range of distance, and it keeps going and keeps going until it reaches a point where it reaches the famous parabolic shape that we are used to. So this is the what happens in the entrance region, that the velocity profile is not final, so it starts to, or the shape of the profile starts to change as the fluid moves forward in the pipe, and as it goes more and more forward, the profile gets more and more closer to the final shape, which is the parabolic shape. Again, I want to emphasize that this is for laminar flow. Turbulent flow is going to be a different story. So for the average velocity, you'd see that, of course, the average velocity has to be the same everywhere. If this is of course, if this is an incompressible fluid, and in case of steady state, in a constant cross-sectional area. So if these three conditions apply, then the average velocity has to be constant, because it's the mass flow rate over density over area. So if the density, area, and mass flow rate are constant, then we will have constant average velocity. So in the beginning, the average velocity is the same as all the velocities, and as you go forward, the average velocity becomes less than the velocity in the center, and so on until it becomes like this. So this is how the velocity profiles develops from constant velocity everywhere to the parabolic shape that we are used to. So the layer of the fluid, and this is an important thing, and let me take a look at this figure here. So this figure is the same as the figure above. It's exactly the same. I just drew this myself so that we can go step by step and understand how the velocity profile goes from here to here. But at the end of the day, this is the shape of the velocity profile, or the yeah, the velocity profiles. It's the same thing. This is the same as this is the same as this, and so on. But the what is different in this figure than the one above is that we have here what we can see as this red line that takes this shape. And if you look at this line, you will see that it splits the area into two regions. A region that has constant velocity, like this, like this, like this. So the velocity is constant. I mean this black line here, this black line here, and this black line here. This is where the inner region, it's the region that has a constant velocity profile, which means that it's not affected by the shear stress of the fluid with the wall. While the region above and below is the region where the velocity profile is not constant velocity. So there is a change in the velocity as the fluid is going from the wall to the center. So this is what we see here. So the region or the region of the flow, or the layers of the fluid that are affected by the shear force with the wall are put in a layer that has a very famous name that's called the boundary layer. So this red line is what we call a boundary layer. So the boundary layer is the layer of the fluid from the wall upward, or to the center, just to make it general, from the wall to the center, that is affected by the phenomena let's put it in a general way. It's affected by the phenomena at the walls. So in case of fluid mechanics, it's going to be the friction. So it's the shear force of the fluid with the walls of the pipe. So this is where the fluid is affected. Now here it's not affected. Here it's not affected. And of course, in the beginning, none was affected. So the boundary layer thickness was 0 in the beginning, and it keeps increasing as the fluid moves forward. Okay, so this is for fluid mechanics. In case of we see and this is why we call it hydrodynamic boundary layer, because this is the boundary layer that relates to fluid mechanics. We can have other boundary layers. If let's say, for instance, in heat transfer, you have a hot surface, the walls are hot and the fluid inside is cold. So we'll have something like this. We'll have a boundary layer where there are parts of the fluid that are affected, which are adjacent to the surface, that are affected by this temperature, and parts of the fluid that are not affected, which is the part in the center. So we'll have a thermal boundary layer, and we'll have a mass transfer boundary layer. So it depends on the type of phenomena we're interested in. We'll have different boundary layers, but in general, just to have a general definition of a boundary layer, it's the layer of the fluid that's adjacent to the surface that is affected by the phenomena at the surface, which is in our case the shear force with the wall. Okay, and as you know, for the laminar flow, the whole area will be affected. So the boundary layer would be the radius of the pipe. Okay, so this is what's written here, that in the boundary layer region, the viscous effects are significant. And the irrotational or core flow region, which is the region that's beyond the boundary layer, it is the frictional effects are negligible. The velocity is constant in the radial direction. So this is يعني something that we need to know about the entrance region. So the entrance region takes a distance where the fluid velocity profile will transfer from a constant velocity profile to the fully developed profile. So the region or the distance the fluid takes from the beginning until it reaches the fully developed profile, we call it the entrance region. And what's beyond this, the velocity profile will stay the same no matter how long the fluid is flowing. And this is what we call the fully developed region. Okay, so this is what we need to know about this. So now the question, why are we interested in studying the boundary or the entrance region and the boundary layers and all these things? The importance is that the velocity profile at the wall, which is, I mean, if looking closely here, you'd see that this is the velocity profile, how the velocity is changing with the distance from the walls of the pipe. So the shear force or the shear stress at the wall is related to the slope. So in a case like this, we'll have a lot of shear stress because we have a lot of change in velocity in a very small distance. This is a very small distance. Okay. And if you recall the Newton's law, it's the shear force is inversely proportional to the distance. It's mu du by dy. So if it's a Newtonian fluid, dy is this distance. So this is very small, so the shear force is high. While at the wall, I mean, in the fully developed region or closer to the fully developed region, we'll have the velocity changing over a long distance. It's almost the whole radius of the pipe. So in this case, the shear force at the wall is going to be small. So how does this relate to the energy losses or the pressure drop? It's exactly like having two cars running very quickly and then going to stop suddenly. So they hit the brake suddenly. One of them stops after short distance and the other stops after long distance. So what causes this fluid or this car to stop after short distance is that the friction between the tires and the street or the ground is very strong. So this very strong friction causes a lot of energy losses in very small time or small distance. So this means that there is a lot of energy loss here. Okay, it has a lot of kinetic energy, and then the kinetic energy is lost very quickly. So the losses are much higher than these where it's losing the kinetic energy kind of slowly. So the friction is less in this case. So the friction here is equivalent to the shear force here. Okay, so the shear force is the friction between layer of the fluid and the pipe or the inner wall of the pipe, the same as the car and the ground. And the velocity change is the same as the velocity change here between here and here and here. And this distance is equivalent to this distance from the pipe wall. Okay, so as the change in the velocity happens at a very small distance, it means that there is more energy losses and more pressure losses than what will be in case of losing the energy over a larger distance. Okay, so that's why from this we can understand that the pressure drop is higher in entrance region of the pipe than in the fully developed region, and that's why we are interested in studying this. So the length of the energy entrance region varies because it depends on different factors, on the fluid properties, the flow regime, and on different things. So it's the hydrodynamic length can be it's kind of got experimentally, but for laminar flow it is approximated as the hydrodynamic length over the diameter is 5% of Reynolds numbers. Okay, and remember that for laminar flow, Reynolds number is around less than 2,300. Okay, for the turbulent flow, it's the same ratio, which is turbulent. I mean the hydrodynamic length in turbulent flow over the diameter equals 1.359 almost equal, 1.359 times Reynolds per 0.25. But if you look here, you see that Reynolds, it's the fourth root of Reynolds number, so it's a very very small number. So from this you can expect that this will be smaller than this. Okay, so the hydrodynamic length in turbulent flow is much less, and it's expected from the the nature of turbulent flow that it gets developed much quicker than the laminar flow. Okay, so this is the what we need to know about the entrance region. How can we calculate the pressure or energy losses in case of or in entrance region? This is something we will discuss later, but for now this is just something we needed to discuss and understand, so that when we go later to the calculation of the losses in entrance region, so we know what we mean by this. So I'll stop here and continue next time, inshallah. Goodbye.